to the second part or your Thursday section of the workshop on social physics. Yeah, my pleasure to introduce you Alexandre Martinez from USP Ribeirão Preto. He's going to talk to us about thermodynamics applied to game theory, the study of the risk associated with cooperation in public goods games. Alexandre, please.
Good morning, everyone. I would like to thank the organizers for the opportunity to present the things we have been done here in Ribeirão Preto. And I was thinking when preparing this presentation, maybe I could have changed the title of it to what is the risk to be nice when people are mean. And the idea of this talk is to be rather qualitative and rather general and show that maybe we are not considering everything we could in game theory. The main concept I want to stress is the cooperation risk. This study has been done by Gilberto Nakamura and Guilherme Contenzini. Guilherme is now participating of this meeting, and he's in Canada, and Gilberto is in Riken Institute in Japan. In fact, he was not allowed to go to Japan, and he has remained in France, in Paris, for a couple months. And I also would like to acknowledge the support of CAPES, CNPq, and mainly of INCT complex systems. The later postdoc scholarships has been due to INCT complex systems. Okay, I'm in Ribeirão Preto, and my institution is Faculdade de Filosofia, Ciências e Letras, Ribeirão Preto. Our lab is in the physics department, and Ribeirão Preto is known for the good beer we have here. And these are the authors who did the hard work. So Gilberto is in the back, and Guilherme is on the front, and they are pretending they are not drinking the beer because it's lunchtime. And what I will talk about, it's about the results of this paper, cooperation risk and Nash Equilibrium. In this paper, we consider a particular situation of public good games, and we show the transition to cooperation and all the nice things concerning the emergence of cooperation. But in this presentation, I want to focus in the dust we have swept below the carpet. I want to open up the points that maybe in the paper is not very clear, and I would like to show that maybe we're missing something, and we should care a little bit more about the risk of cooperation in establishing a direct connection with thermodynamics. So the outline of the presentation is we have this question: are we using all information we have in game theory? And I will start recalling the ideal guess. Then I will consider two-player, two-strategy games, and I'm going to compare with the Ising model. And then we extend the idea to n-player games. And some considerations about cooperation risk, and we stress the evidence of this concept of cooperation risk in a particular kind of game that is evolutive potential games. Then, doing this, we are able to set up a natural connection with the thermodynamics and only considering the cooperation risk. If not, it's not possible. So let's start recalling what we have in an ideal gas. We have, for instance, Clapeyron equation, where with it we can do a lot of things. You know, we can do a lot of improvements in steam machines using this equation. But notice, this is a state equation, and it has only partial information about the system, in the case, the ideal gas. We have another state equation, that's the equipartition law, that it describes another kind of experiment that can do with the ideal gas. So when you put together the equipartition energy law and the Clapeyron equation, you can write the entropy of an ideal gas, and this entropy, it certainly has all the information we need to describe the ideal gas. It's kind of, we have put together all the information we know about the ideal gas in this function, that's the entropy. Nevertheless, the entropy is not a very nice quantity to work with. A more handy function that keeps all the information of the system is to use a thermodynamic potential, a free energy. Why? Because when you change something inside, you can predict the new equilibrium state by minimizing the potential. So, minimization principle is very good and very handy to use in thermodynamic potentials. Okay, and this is the idea. We want to use minimization thinking to find equilibrium, to find steady-state properties of the systems we are going to consider. In the case, there are games, you know, game theory. The thermodynamical potentials are the most handy way and optimized way to deal with thermodynamic systems. And for each instance, you have its own potential that's handy to use. Okay? The idea is to try to describe games using statistical models. And we're going to start very simple with only 2 players and 2 strategies. So again, in a game, you have a conflict. The best thing to do is to cooperate. That's the global minimum of a potential, but the chooser's choice is not to cooperate, it's to compete. And this is known as the Nash Equilibrium. Okay, so it tries to maximize each agent, each player tries to maximize its own interest, not regarding to the others, okay? So this is mainly the main idea behind the Nash equilibrium. So in these games, you have four quantities. That's the temptation not to cooperate, the punishment if you cooperate and the other does not, if you do not cooperate and the other also does not cooperate, the reward, what you gain if you cooperate, and oh, I put twice, and the sucker. The sucker is the guy that cooperates, but the partner cheats and he loses. And you can establish some inequalities between these quantities. And then you have several games with several conflicts. And you have the stat hunt game, the prisoner dilemma, the cheating game. It depends on how these values combine among themselves. The point is that you can put this mathematically by means of a payoff matrix that you can count how much each player gains or loses according to the strategy it has. Okay? And the solution to these dilemmas are the Nash equilibrium. Okay? So the tendency is not to cooperate when compared to cooperation, although cooperation is the global minimum. So this is the point in the game theory. So here I'm going to be a little bit careful. So we can count the gain of player one, thinking that in two strategies, cooperation or not, okay? And these strategies are represented by the values of the variable B1 and B2. B1 concerns the strategy of player one, and B2 concerns the strategy of player two. So if both cooperate, we have rewards R. If one cooperates and the other not, it depends if you have T or S. And if both do not cooperate, you gain P. So we can rescale, change variables, and try to put these equations in a simpler way and using these reduced variables, T, S, and see that we could be able to get rid of P and R because they are not very essential quantities to what we are looking for. So we can now add the gains of the players, and we have the total payoff. And the total payoff, I stress that we have a two-body component and two one-body components term. So this two-body components means the interaction between the players, and the one-body component means it's kind of an external field applied to the system. We can see like this. To get more intuition, we can change the Potts variable 0 and 1 to the Ising variable -1 and 1, and things become much more clear, much more clearer. So if we define an energy for two players, E2, this quantity, this factor regarding the interaction between players, we call J, and we put aside the external field, and here we see we have a problem. For two-player games with two strategy, we have an energy that's very similar the one of the Ising model. Nevertheless, we only have one parameter, J. Okay, so S1, S2 are strategies. And then if we have the ferromagnetic case, we have a stag hunt game. If we have the anti-ferromagnetic case, we have the chicken game. And here is very curious. The prisoner dilemma can be both. Sometimes you can use J greater than zero, and sometimes you can use smaller than 0. And when you compare to the Ising model Hamiltonian, you see that it compares, but not very much. It compares very well with this two-body term, but it does not compare well with the field components. See, in the Ising model, you can make the magnetic field, the external magnetic field, go to 0, to vanish. Here we cannot with the game theory Hamiltonian. So this is and these points that maybe something it's missing here. If we want to correct this and have another parameter, we have to add up something here that depends on the values of each player. Okay, we can generalize this idea to any player on a graph in order to see phase transitions and things like that. So we can consider a very general graph, and we can do the calculations, and we see we have the same stuff. So the two-body interaction, it's okay. Game theory deals with it, but the field, external field term, does not work very well, because in the Ising model, we have the parameter that it's 3, but it's fixed in the game model. So, what can we do to deal with that? It seems the payoff in game theory brings us only partial information as the Clapeyron equation in the ideal gas. State equation is not a fundamental one. Okay, so what it means is that using the payoffs only, we have like a Clapeyron equation. We can do a lot of things in game theory, but you're still leaving something beside if you want to look in thermodynamics point of view, which can be interesting. A simple way to fix things up is to add a quantity by hand that depends on n. Okay, and in order to have an additional external field here. Okay, but what does additional information mean? It is the cooperation risk. Okay, what is a cooperation risk? The cooperation risk is when one agent cooperates with the other, but the partner does not cooperate. So it's the risk of being a sucker in short terms. It's a concept that has been introduced by Nash in a qualitative way. It remained intuitive for decades because it's very hard to quantify what's this risk. In fact, we are not aware of any other paper that quantifies this risk. Okay, and it it shows up clearly in evolutive potential games. In evolutive games, all players choose the best strategy, okay? But in potential games, they randomly choose the strategy. The best strategy, it's the most probable one, okay? So this is the trick. We are introducing stochastic factors when the players choose strategies to play the games, okay? So here I'm concerning very general games. And this is an idea that has been put in the mid-90s. So what happens? The choice of a strategy depends on a random factor that we put it as a beta inverse of the temperature, and the probability to choose the best strategy, it's an exponential one, okay? It's like the potential of the strategies are distributed as the energy in the statistical physics problem. And if we sum all over the configurations, we have the partition function, and as in statistical physics, if we work with the partition function, we can get all the information about the system. Okay, so here is the connection, the true connection between the potential games and the thermodynamics. Okay, what happens? What usually happens? The potential US is taken to be the total payoff. And when one does that, there's a well-known issue. Nash equilibrium configurations are not the minima in the potential. And people who have worked with that know this. And for a long time, this has been put aside. But if we think like this, we are building the potential only with a partial information of the system. Maybe there is something else. So to fix this issue here, to bring the Nash equilibrium to the minima of the potentials, we can do it very simply. We add a chemical potential to this probability. So we use US as the gain plus risk. Players, they favor gains over risks. It's equivalent to say that in thermodynamics, we are more interested in the work we get from the machine than the heat it sends abroad, okay? So it seems that in game theory, we are looking only to this part here, the work done, and we are neglecting something like the heat dissipated. We all know if you want to have the conservation of energy, the first law of thermodynamics, we have to consider both. So what we have done? We have considered a particular game, in the case public good games, and in this game we were able to quantify what is the cooperation risk. So I think one of the good things and the innovations of that paper is that for the first time, the cooperation risk has been quantified in game theory. And
5 minutes to go.
Okay, I'm finishing. So, of course, when you work with potential games, you have to work with averages, thermal averages, okay? So this is the idea. So this constant that we have add up to the potential, game potential, it's exactly equivalent to the constant we have to adapt to two-strategy games to have an equivalence with the Ising model. Okay, so finishing. So we've been working with evolutive potential games without cooperation risk. And this is more or less equivalent to work with the Clapeyron equation in ideal gas without considering the equipartition theorem. Okay, it works for some systems, for some experiments, but it does not work for other experiments. The evolutive potential public game with punishment makes a cooperative transition appear. It emerges in a very well-defined temperature. Independently of the game played, the cooperation risk is a one-body quantity, and each player carries along, and it has been often neglected. So, what we would like to do to understand the role of this quantity in other games. So, I thank you all for the attention, and maybe we can go for questions.
Okay, thank you, Alexandre. I'm seeing one question in the chat. Can you read it, please? The last one, last comment.
Let me see if I can.
Okay.
It's not clear to me if somehow you are considering the total pass. Yes. What one usually does is exactly that. You take the total payoff and you put it as the equivalent of thermodynamic potential, and it's not.
We cannot hear you.
You cannot hear me, Mark?
No, yeah,
okay.
already. Now it's working. Are you trying to put your slides back?
My slides? I'm sorry, Marcus. My slides? Okay.
You have just 1 minute, perhaps. Okay.
Okay.
I'm sorry, Alexandre, but you're trying to answer the last question, or you are done?
It's not clear. Yeah. It's Gomez asked it's not clear to me if somehow you're considering the total payoff as a kind of energy of the system. Yes.
Alexandre, I'm really sorry, but we're just on time, so perhaps you can answer to that question directly to the chat. Huh? You okay?
Okay. Thank you, Marcus.
Thank you very much. So next speaker is going to be Sina Sajjadi. I'm sorry, Sina, I don't know if I pronounced correctly. Yeah, Sina Sajjadi is going to okay, social distancing.
Can you hear me now?
Yeah, but I cannot see your presentation.
Yeah, I will.
Okay. Oh, yeah.
Yes.
So we take Sina Sajjadi from Sharif University of Technology. He's going to talk to us about social distancing, pedestrian dynamics, and its effect on disease spreading. Please, Sina, you have 50 minutes.
Thank you. Yes, well, now this first slide is redundant.
The sound is too low. The sound is too low.
You cannot hear me now?
No, it's very, very low.
Okay, let me just adjust it here. Is it better now?
No.
I'm sorry. It keeps going. Is it fine?
Okay, just only a little noise in the background, but now I can hear you. Maybe.
Okay, I hope it doesn't toggle back. Okay.
No, it's okay. I mean.
Okay, working.
Thank you.
Thank you. So yes, we are presenting a model on how pedestrian dynamics and infection spreadings go together.
I'm sorry, but again, I cannot hear you.
I don't know why this keeps going back. This is. I don't know what this keeps happening. It's very unfortunate. Let me stop sharing and share again. I don't know how I should. You know, where should I check it? Okay. No specific options for this. Okay. I hope it remains high. No, it doesn't. Yeah. Okay, what if I speak a little bit louder? Is it better now?
No, a little too low.
This is unfortunate. Let me change another, switch to another headphone. Okay. I switched my headphone, but still. Okay.
Oh, I have a suggestion. Maybe if you don't mind.
Sorry, could you repeat?
No.
Okay, I will join with my other device now. maybe if we could proceed with the next speaker, then I'll could come back.
I cannot hear you.
Maybe if you proceed, maybe I could come back with my other device.
So you are proposing switch with another speaker. So you're
Yeah, the next one if possible.
okay. So if okay, that's a good solution. You can exchange now for the next speaker. Let me see.
Yeah, it's me. I'm ready.
Is Nagi? Are you? That's okay for you, Nagi?
Yes, but yes, I still hear some noise. Do you hear me?
Yes, there's some noise background.
Yes, I'll try to share my screen.
No, now it's better. Now it's better.
Okay, okay. Do you see my screen? My presentation?
Yes, I can see it. I'm sorry to everybody about that, but
okay, that's okay for me. Don't worry.
Okay. So let's talk. Now we're having this talk by Nagi Khalil from Universidad Rey Juan Carlos. He's going to talk about continuous opinion model inspired by the physics of granular gases. Please, your word.
Thank you. I thank the organizers for the opportunity to present my work. So all the results I'm presenting in a few minutes are included in this reference at the bottom of this slide. Okay, the motivation of the work is the connection I found in the literature between continuous opinion models and the modeling of granular gases in one dimension. I will try to clarify the analogy and maybe differences, and then to take advantages of the analogy to study the evolution toward consensus in this kind of model. So my model has 8 agents or nodes. So the agents are on a network. So that represent the social interaction. Each node, say I, has an opinion Si, which is a real number between minus infinity and infinity. And the state of the system at a given time is say the collection of all opinions. So the dynamics is as follows. I take 2 nodes, I and j, with a probability per unit time, which I call pi, and it is essentially proportional to for now a generic function of the opinion difference of the 2 chosen agents. Okay, it only occurs when the 2 agents are connected, so that I introduce here the agency matrix. R is not only a parameter here, a positive constant. So once I choose the 2 agents, then they interact. The social interaction is like the one written here. So it's like a collision of two particles. So after the collision, yes, or the interaction, the new opinions are is prime, denoted by prime, or by this collision operator BIG. So it's essentially a linear combination of the previous opinions. Here appears a new parameter, mu, which is the so-called persuasibility. And when mu is equal to 0, there is no change of opinions. And while for mu equal to 1, there is an exchange of opinions. Okay, this is a general model and includes as a one case is the found model, which is a very well-known model in this context. And also I try to generalize it to try to mimic in some sense the Volter model in the sense that it includes also the copy mechanism. This limit is when mu is equal to 1 or rho is equal 1 to 2, 1, 2. So, but in this case, it's a bit trivial because only the 2 agents interchange the opinions. So globally, the system doesn't evolve. Okay. So here I show you the main properties of the model. All properties are a consequence of the collision or the social collision rule. So the total opinion or the sum of the opinion of the 2 agents that interact are conserved. After the collision, the sum of the opinions after the collision is the same as before the collision. We only have one consensus state that can be reached or not. And this consensus state is when all agents have the same opinion S bar, which is the average of the initial opinions of all agents. And this is important. The approach to consensus is characterized by the tendency or the losing of opinion energy. I define the opinion energy as the sum of the squares of the opinions. Okay, so after the collision minus before the collision, this is a negative or null quantity. Okay, for mu equal to 0 or mu is equal to 1, or if the two opinions are the same after the collision, there is no change, but in other cases it's a negative. Okay, so here comes the analogy with the granular gases. If I identify the opinion with the velocity of a particle, and I write the mu parameter as a function of alpha, then this alpha turns out to be the so-called coefficient of normal restitution. This is a coefficient that measures the loss of energy when two particles collide. It's not a molecular gas like usual, but it's a granular gas. Granular grains lose energy when they collide. Okay. In fact, the previous three properties that I mentioned are related to the conservation of linear momentum, the existence of a state of zero temperature, where temperature is a measure of the kinetic energy, average kinetic energy of particles, and the third one is the dissipation of energy. Okay. However, the two models or the two systems are inherently different. While the opinion model is stochastic, the granular gas is deterministic. The grains are obey Newton's law, if you like. Okay, so in order to clarify this point, I consider the mathematical description of the opinion model. So I start with the most general quantity, or the one which has all the information of this system, which is the probability P of a state S at time t. And then, according to my dynamics, this is this quantity obeys a master equation, where here B is the inverse operators, the one appeared before. So from this master equation, I can take or get all the quantity in principle, which are less general, like the probability of finding node I with opinion S at time t. Okay. It turns out that the equation for this quantity is not closed. It is very usual in stochastic processes. So this equation also appears the probability of finding two nodes for given opinions Si and Sj. And then to quantify this quantity, I have to consider its equation. Then the free body correlation appears, and so on. So it's very complicated. And then what usually one does is to propose a simplification to close this equation. I will do that in the following, but first, let me say that I can take some exact results from the master equation. For example, I can demonstrate that the mean opinion, defined as follows, as the average over all opinions of all agents, is constant in time. And the approach to consensus can be fully characterized by a new variable that I define as opinion temperature, in analogy with the temperature of the granular gas, which is the average of the second moment of the opinion. Okay, and this is the exact equation for the fact with the exception, or the problem is that this quantity, that appear here on the right hand side, the so-called cooling rate is not implicitly known because the Pij appears here. But if this quantity is positive or null, so or zero. So that means that the temperature, this quantity that measures the approach to consensus or not, or the approach to the steady state, is always a decreasing function of time. So, okay. And moreover, this quantity can fully characterize the consensus state where all agents have the same opinion or equivalent of the temperature to be zero. However, we can reach an absorbing state or a steady state where T, the temperature, the opinion temperature is constant, but not zero. So not in general, we don't know in general reach consensus. One exception is when this probability of interaction are positive when the opinion differences are different of two agents. Then in this case, yes, we can identify consensus with absorbing states. So there's only one absorbing state and is of consensus. Okay. So now I will try to simplify the kinetic equation I mentioned you before, this one here, by the simplest approximation, which is the so-called mean field approximation that are included into these two assumptions. Then, and at the end, I end up with this equation where I, instead of writing P, the probability of finding any node at opinion S and time T, I use this F, which is the partition function, which is more usual in kinetic theory, which is essentially P multiplied by N, the total number of particles. So this is quantity is the mean number of particles with or agents with given opinion at time T. And then this equation is closed. I can solve it in principle. And this is the Boltzmann kinetic equation, okay? And now I understand, we can understand the analogy between the two systems. They have different microscopic dynamics, but the mesoscopic dynamics, the one given by this equation, are the same, okay? So, yes, in the following, I will try to solve this equation for a particular case where this probability transition or collision, sorry, is proportional to the difference in opinion, the beta power of the difference in opinion. This is traditionally this is a trivial case in the sense that the final state will be, according to the result I have shown you, is the of consensus. Okay. However, here the interest is not in the final state, but in the evolution towards this state. So if I choose this probability, I introduce a new parameter beta, which is here, and alpha. I remember you that controls the social interaction. So alpha equal to -1 is no change in opinions, while alpha equal to 1, there's a interchange of opinions. Okay. So now I use well-known results from kinetic theory of granular gases and can propose a scaling solution to this distribution function, the solution to the Boltzmann equation, in which all time dependence occurs through this prefactor here and through this quantity C, which is a rescaling opinion. Okay, this C0 is it depends on the granular temperature, which I defined before, which is essentially the second moment of this distribution function. It turns out that the equation for this scaling function phi doesn't depend on time, the equation, and can be solved. Okay, for beta equals 0, it can be solved exactly. This is a unimodal distribution function. It has only one maximum. That means that the approach to consensus for this case of beta equals 0 doesn't depend on alpha, on how is the interaction between the agents, and this the approach to consensus, the approach to a delta function is through a unimodal distribution with one peak. I will show you how it is. For other cases, beta greater than 0, the situation is not that easy. Okay, and in the result I've shown here, in the bottom you see two plots of the same plot here, normal here, normal, when beta is equal to 0 for different values of alpha. The symbols are Monte Carlo simulation results, and the line is the theory. While for different values of alpha and beta here in this panel is for equal 1, and alpha is different values. Then for alpha small enough, I have a unimodal, like in the previous case, one maximum. But if alpha approaches to 1, and this doesn't depend on the sign of alpha, this is very important also. So this means that when the social interaction is weak enough, this scaling function develops to maxima. Okay, and similarly when I vary beta and fix alpha. So the result can be summarized in a phase diagram where I can identify two phases. For small alpha and beta, I have the approach to consensus through a unimodal distribution, while in the other case, I have a multimodal with two peaks. In between the two regions, I have a collapse of, except for this region, which is not I didn't find a collapse, is a collapse of the data, numerical data, and also it can be seen probabilities are aligned here of theory, approximate theory. Okay, and that's all. Let me say only that this multimodal approach to consensus can be relevant when alpha approaches U1, when the social interaction is weak, because then what happens in reality is the distribution of opinion first develops two maxima, and then these two maxima becomes closer and closer. But the approach to the develop of two groups of different opinions can be faster than the approach to consensus as a whole. Okay, and there are more, let's say, conclusions here you can read. But I want to leave one minute for questions if you like. Okay, that's all. Thank you.
Thank you, Nagi. If there's any question, please use the chat because we are already late for the schedule. So thank you very much once more, Nagi. Let's please, can you leave the sharing mode? Then now we are coming back to Sina. Apparently,
hello. Can you hear me now?
Yes, perfectly.
Okay, I'm sorry.
No problem.
And thank you for waiting. Okay, so yeah, you can see my screen.
Go already. I think I already introduced you.
Yeah, that's great. Humans gather around each other for different purposes, and in each type of gathering, there is a specific risk of being infected with a spreading disease. We would like to calculate this risk in some specific settings, try to figure out how we can decrease this risk, and also what is the cost of decreasing this risk. So we have a agent-based model, has a mobility compartment to it. So we consider several pseudo forces which governs the mobility of these agents. For example, here, this agent I has this first type of force, personal force, which at each time steps makes it current velocity VI to be aligned more towards its desired velocity, which is directed towards its target at a time. There's also another type of force borrowed from pedestrian dynamics, which is a social force. So it has this exponential forms, and it bars agents from colliding into each other. And as we can see, there's this sigma here. So we have defined that in this way. So this sigma is also responsible for the range, and it's responsible for the intensity of this force. And it will be something important that we'll come back to it in our analysis. And there's also another type of force, which is the force which bars the agents from colliding into the barriers of this system. So this is the mobility compartment, but the spreading compartment is like this. We have three different states regarding to the disease: susceptible, infectious, and exposed agents. So we have this type of direct transmission where infectious agents interacting with susceptible agents with a probability convert the susceptible ones to exposed. And the second method, indirect transmission, is when infectious agents interact with a clean environment, like a tile in our setting, and turn that clean environment to a polluted environment. That polluted environment, in turn, will turn a future susceptible agent interacting with that tile to an exposed agent. So we have the governing forces of the mobility, and we also have the spreading. So I will show you an animation. Can you see the animation now?
Yes.
I assume. Yes. So here we can see this specific infectious agent is going towards their target, and they're trying to avoid to some extent to not to collide with other agents. And as the time progresses, we can see that agents are getting exposed via both direct and indirect transmission. Okay. This is our software. You're very welcome to interact with it or propose modifications or generalizations. So now our most specific parameters are the number of agents in our confinement, the intensity of social distancing, or the sigma, the probability of direct and indirect transmissions. So this sigma can be thought of as a toggle, which decreases the social distancing intensity of people, like how much they would like to be farther from each other. And when we increase it, the total population will try to stay farther from each other. So here I have the percentage of people who got infected for each specific value of sigma or social distancing. So as we go to the right, we are increasing the value of social distancing force. The first figure is the fraction of agents who are contaminated by direct transmission. So as we can see, by increasing the sigma, there's a drastic drop in the proportion of people who are going to get infected through this direct transmission. In the lower figure, we have the proportion of agents who are infected through indirect transmission. And it's very counterintuitive because initially this value is increasing and after a while it starts decreasing. So why that could be? If we look at the mobility parameters of our model. So the first figure, the x-axis is still the sigma. And I think I didn't mention this, the two colors indicate two different densities of population in the setting. So the first figure, for the first one, we look at each agent, we look at their nearest agent and calculate the distance, average this over time, and also across all agents. And this value is increasing with sigma, and this value is related to the probability of getting infected toward direct interaction. But the value in the lower figure indicates the average distance from the center of the system. And counterintuitively, when we increase the sigma, initially this value decreases. So when we increase this social distancing intensity, we can see that people are gathering around in the center a little bit more than the situation where we don't have social distancing. And it's really correlated with the probability of getting infected towards indirect transmission. But after a while, we can see, yes, but when we increase the sigma, it will also increase this distance from the center, the average distance from the center. But in turn, why is this again? So this schematic in the left tries to explain this phenomena. So the pink case is when we have a very low or zero social distancing, and agent AI is an agent which is trying to get to their target and is faced with a swarm of other agents. In this case, it really doesn't care about the other agents, goes straight to the target because it doesn't feel them actually. After that, we have this gray value, which is a little bit social distancing, but not quite enough. So we can see that they go into the swarm, they hit everyone, they get breaks, the speed gets decreased, and they stay in that swarm-like gathering for a longer period of time. So if we take snapshots, we can see every agent in the center more than the previous setting. But when we increase this intensity of social distancing to very higher values, like the yellow, we can see that actually people do not enter the swarm, so they go around the swarms. That's why after a while, we can see that this distance from the center is increasing. And the figure to the left is trying to support this argument, as we can see for the purple one and also the yellow situation. We can see that as we go further from the center, the speed of agents is decreasing, but for the gray situation, which is this middle very weird value, we see an increase in the speed when people go to the peripheries. So when we move from the center, actually when we move toward the center, we are decreasing our speed, contrary to the other cases. So in the interest of time, I would skim through the rest of the paper. So we also consider two different situations where some people are abiding, but the rest are not abiding. And here we see two different plots. So the green plot is the situation where the infectious agent itself is not abiding, and the khaki version is when it is abiding, and it has the most drastic effect compared to what other infectious agents induce on the system. We also changed the disease itself, so we changed the probability of infection of both direct and indirect transmission, and we calculate the difference between the severeness of these two types of infection. And I think I'm on time. So in general, we considered pedestrian dynamics plus a contagion spreading. We added social distancing as a changeable value in our model, and we analyzed its effect on disease spreading. And this is our paper. I would be glad to have your feedbacks on the paper, and more details can be found there. Thank you very much, and sorry for the initial disturbance.
Oh, thank you very much. So I suppose we have time for one or a couple of questions if you quickly. So I'm not seeing any question in the chat. No questions. Oh, there's a question. Can you see it, Sina?
Can you tell me?
Yeah,
yes,
I
yes.
can read it for you. Very nice talk, Sina. Can you tell me anything about size and effect?
Yes, yes. As we can see, well, more condensed situations are making people more probable to getting infected. But the other issue is that when we change n, when we increase the density of people, the system itself gets more sensitive to change. So as we can see in this plot, when we change this value of sigma, it has a more drastic effect on the orange case where it is more crowded. So both more infection and also more sensitivity to social distancing.
Okay. Any more questions? Oh, there's one more. Can you read it?
What about if one assumes there is a distribution of probability of individual transmit disease to others? Yeah, that is a very interesting question, but this is perhaps one of the first studies in this direction. That would be an interesting thing to study. But generally, when people start with an agent-based modeling, usually we have this: everyone is the same, every person has the same health issues, and yeah, that is true. Well, if we want to get more realistic, we have to also incorporate that.
Oh, okay. So since I don't see any more questions, I thank you very much again for your presentation. We should move on. Last speaker is going to be the last one before the post-session is going to be Francisco Lima. Francisco, please, could you share the screen with us?
Okay.
I can't see your screen yet. Oh, yeah. So now the last talk before the coffee break. Now you have the Francisco Lima from Distrital for Computational Physics Lab, Department of Physics, Universidade Federal do Piauí, and he's going to talk about majority vote and the BCS model on complex networks. Francisco, please.
Okay. Thank you very much for the invitation. And my talk is about two opinion formation models, majority vote model and BCS model on complex network. We have a brief review about these models. In 1992, Oliveira, based on Christian criterion, created a version of the non-equilibrium Eisen model, called majority vote model. Oliveira simulated the majority vote model in a square lattice and found the same exponent for Eisen model in 2-dimension. Here we have again simulation majority vote model, but now on the complex network called Erdo-Renier-Handel graphs. The results about the exponents are different the previous exponents and depend on the network connectivity. In the same subject, Lima et al. Have also studied the majority vote model, but now on directed Erdo-Renier-Handel graphics. Okay, bom, good. The results showed that exponents depend on network connectivity and are different from the previous results and suggest the found new universality class for complex network. Okay, in 2012, Biswas-Chatterjee-Sen created a connected model of opinion formation that we call the BCS model. The simulation on infinite dimension found the results about the exponents belong to the mean field universality class. In 2016, Mukherjee and Chatterjee studied the same BCS model, but on 2-dimension and 3-dimension, and the results about the exponents are the same of the Eisen model in 2 and 3-dimension. Is identical. After that, Lima and Professor Plaska studied the BCS model on direct Barabas network, and the results shown that there is other universality class for BCS model on this complex network. In next, the BCS model now were studying the normal Barabas network, and the results for the exponents are identical for main field, universal class main field. And the simulation, Alves et al. Used the continual opinions for BCS model. In the same year, Lima et al. Studied the BCS model, but now on a Polonium network. And the results about the exponents depend on the probability P of the network links redirection. And again, suggest a new universality class. Here in this slide, we have some variants about the BCS model. When the author is Nuno Trokidakis, and there's others. Here we have a dynamic evolution for majority vote model. So initially we have a spin variable sigma with values plus minus ones at each node of the network, and each time step we try to spin flip a node. The flip is accepted with probability or equation master double I sigma that depend the sigma, the variable state, the E site, and also the neighborhood, neighborhoods that about the has a signal function for contribution the neighbors of the central site and on my square lines. The Q is here identical to social temper like Eisen model, and the central site sigma I can follow the neighborhood majority opinion with the probability Q, and the majority sign with probability P equal 1 minus Q. The signal function is equal 1 if X is bigger than 0, or 0 or if X equals 0, or minus 1 if X less than 0. And in the slide, we have a representation of the behavior, the signal function. When the signal function is identical to minus 1s, we have central site blue, and the neighbors, the majority neighbors are red in time tau. As we can see, in time tau plus 1, or next time, the central site that is blue here take the signal of the most neighbor, where the most neighbor are red and have minus 1 sign. Now, in the next case, where the signal function is equal 0 in time tau, as we can see, we don't have majority of neighbor with any sign here. So in the next time, tau plus 1, the central site may or may not update its signal with 50% probability. In the case, the central site no update, and here central site update. In the last case, when the signal function is equal 1, here the central site is red, and most neighbor are blue, and again the same. The first case, the central site takes the sign of the majority opinion or majority neighbor. And next, we have now BCS model. Here we used the discrete opinion, the BCS model on the original BCS model has continual opinions. Aqui, or here, we consider the discrete opinion in our study on complex network. Okay. Different of the majority vote, here we have the pairwise interaction. Okay, and dynamic evolution is as follows. First, for each network site, one agent or individual is assigned with discrete opinion variable OIT between on three values, -1, 0, and +1. And set for each time tap, we handle select a network site to be updated. Next, the handle next we handle selects only one of its bond and choose the affinity μij of the bond for each pass of the dynamic. Here, the affinity parameter μij is discrete variable and assume a value +1, which can be turned a negative with a probability Q. Q is identical in the majority vote model. This is a noise parameter that work as temporal social temper. Okay. Next, we have two sites, I and J, that share the select bond, are updated according to the following. To equation 2, equation 3. Is the OEG T +1 is updated stage that depend on the stage OIT plus μij and the opinion of the site J site. Okay. In this case, the opinion for both sides are updated at the same time by equation 2 and 3. And last case, last situation, the opinion states must be in the interval -1 and +1. In this slide, we have the complex network that we use it in the work, that are Barabás Alto Network, Erdo-Reni or Erdo-Renai, Randall graphs, and Apollonia network. This figure is the third generation of the Apollonia network. In this case, A and B. In the A case, is the normal Apollonian network. The black arrows represent all income and outcome links here, as we can see here. And the B, the right figure, we have redirecting the links with the probability equal 0.1. We can see that here has linkings or connection directed with the probability 0.1, and the blue is the connection of the long range, and the red is directed link, and the black arrows are the normal connections. You have the observables, where the opinion formation BCS mode and the majority vote mode present a continual phase transition, and to start each, we treat individual as atoms. So we have the order parameter or magnetization, susceptibility, and Biden cumulant. It's the variables that we measure during our Monte Carlo simulations. And all the parameter and function of the noise key, susceptibility, Biden cumulant. To find the exponents, we used the finite site scaling relation, where the equation H, we can found the beta ni exponents in the relation. In the next equation, we can find the gamma ni exponents. Here we have the results. Our simulation on directed Barabas Albert network is complex network is special because the Eisen model no present phase transition in the network. Okay, here we have the picture with the effective dimension divided by 2. The exponents for both model, BCS and majority vote, where the full symbols correspond to the BCS model, and the other symbol to majority vote model. Here we have now results for directed small world Apollonian network. Here is simulation for the picture. Here, our results are for effective dimension that's next to 1, Here, the exponents ratio exponent beta n, we can see that for p equal 0.5 is a limited case where for p bigger than 0.5, the exponents differ for both models. But
20 minutes already, Francisco.
okay. But about the p less than 0.5, we have the similar exponent both model BCS and majority vote model. And the last case for gamma ni, we have the same behavior for exponents that depend of the probability p. Next, we have result for Erdo-Renai-Handel graphs, both model, but the left picture, we have the case where when the Erdo-Renai are directed. The links are directed, and the right, the link is normal. We can see in both pictures, the results are similar, that are independent of the if the network is directed or no directed. In the next picture, we have now for both models, BCS left and majority vote right, is a curious case, and can see for Z bigger than 20, the exponent for direct network are identical for BCS, but is different for majority vote model. In conclusion, finally, we can see that for both models, the ratio exponent can be in different universality class. Can be Eisen exponent, BCS model, and majority vote on squarelets, and Mills field, BCS model, and Barabas out network with continual opinions, and other BCS and majority vote on direct small world network is the Renai random graph, and direct Barabas network. In the case the opinion of the BCS is discrete and no continuous. He was one of the pioneer in sociophysics, that he was my friend and big master, and Stauffer once time who respond my question about the opinion model. I asked to Stauffer the sentence: is there any sense in calculating critical exponent for opinion model formation model? He answered, yes, according to me, it's if the exponents are different, the mean field, the opinion of the n individual is more important the group where he belongs. Thank you very much.
Thank you. Thank you very much, Fernando. Francisco, I'm sorry, Francisco. Let me see here in the chat. I'm seeing one question. Can you read or want me to read for you?
Yes, I can read you.
The question, that is the last question. I suppose, have you looked at the other networks topologies? I think this is the question.
What is very low, very down some. Oh, okay.
Francisco, are you able to read the chat, or you prefer that I read for you?
Okay. I try to see, try to see chat image about chat. Pause, unnoted.
Oh, Francisco, I think maybe it's better you just read the chat and then you can answer directly, right? Because we are already advanced on time and you are supposed to have a coffee break before the post session. So we'd like to thank you again for your presentation. And for everybody, we are going to be back at 12:30, right? For the last session of the day, which is going to be the poster session. So more or less 15 minutes for coffee break.